Okay, hi everyone. It's good to have a lot of you here and joining us for the um, summer seminar, I guess. So Santu, who is currently a postdoc at Michigan State, a former Wisconsin alumni, he will give a talk on rate of conversion for quasi-periodic homogenizations of Hamilton-Jacobi equation. So please.
Thank you for giving me a chance to talk about the work. And so today I will talk about one of the work that I've been working for quite a long time and recently resumed. All right, so I will kind of repeat the introduction on the background of the viscosity solution. It might be already familiar with a lot of people here. I may go through them a bit faster. And then I'll talk about homogenization and the result on the rate of convergence. Okay, so viscosity solution, as I think everybody know, here is already know, we define viscosity solution using touching from above and below, and for general second order equation. And this is the main subject of the main notion of solution that we'll be working with, and then their connection with optimal control theory, which is the main tool that we use to tackle the problem. Here's a typical example again that we've been seeing so many times, that the Iconal equation. So the equation have infinitely many solution, but there's only one maximal solution, which is happen to be the viscosity solution, and this solution can be recovered by Van viscosity in the equation below, and then we can solve for each epsilon, and then we vanish them. All right, so the connection between Hamilton-Jacobi equation and optimal control theory can be summarized quickly as follow. So if we have a compact metric space, then it will be a control set, right? So a control is a Borel measurable map going from 0 infinity to the control set. Then we're given a velocity vector field B and a running cost. Then for each of the control and each starting point X, we can solve for the ODE that having velocity at time t to be given by B. All right, then the question is, can we minimize the cost functional? There's different way to define the cost function depending on our purpose. In this case, we define the cost function to be the infinite horizontal problem. So we let this run forever, and then we add a discount term, right, to make sure it's finite. Then we can say that the value function solve a Hamilton-Jacobi equation, and the derivation is the definition usually assume U is smooth, but we only have the function is not smooth. So the technique of viscosity solution is used here, and which is classic, right? So now we come into the main subject of the problem, the homogenization, which is I will recall briefly here. Right, so the such thing is studied with Leon, Papanikolaou, and Barahan in the paper, famous unpublished preprint. Right, they proved that for a periodic and coercive Hamiltonian, the possibly non-convex, for each parameter epsilon, when we have a unique viscosity solution U epsilon to that problem, then when epsilon vanishes, U epsilon converted to U, and you solve an effective equation given by UT plus the effective Hamiltonian X bar of du. Then here X bar is the unique constant such that the ergodic problem, right, can be solved with a viscosity solution. So the solution to this equation is not unique, but the constant is unique. So and that is sort of like a nonlinear average of the Hamiltonian, and this has many different names. Effective Hamiltonian from Hamilton-Jacobi equation, homogenization theory, also ergodic constant, or addictive eigenvalue of H, come from sort of like a Hopko transform. Because in dynamical system, they also have many names like the alpha function and minor critical value, which is in WKM theory. So this has this appear in many different places. All right, so here's a typical example in the periodic setting, right? If we have classic Hamiltonian with classical mechanics, potential energy and kinetic energy, here we choose V to be that periodic function. Then in one dimension, we can solve for the formula of X bar, and we will typically see that X bar has like a flat part, right? And this is true for in higher dimension. So if it has a zero, then there's some criteria that we can obtain a flat part. And we'll see later on how this kind of shape of H bar affect the rate conversion in homogenization, and leading to some difficulty that we'll see later. All right, so let me talk a little bit about the heuristic derivation of homogenization. This is already, I guess, familiar with people, but there's a point that we want to point it out. That's why this is important in the proof we do later. So as usual, we will assume x epsilon and x as two independent variable, and then we will introduce an ansatz, right? So the y will be the x epsilon, and then we will introduce an ansatz in epsilon, and then we take the derivative and we plug into the original equation, and then just by collecting all the term, the first order term, the epsilon or inverse order term, will arrive at this equation. So if we fix x and t, then we can define the new constant value as like the following. So that's how the ergodic or the cell problem arises naturally. So from this ansatz, then we see that heuristically, like the solution u epsilon should behave like a u0, which is the solution to the limiting problem at like a epsilon u1, and this will be called the corrector, right? So homogenization is just if you want in the periodic setting, right? So in the periodic setting, usually we can obtain even that u1 is a bounded function because it's periodic. So you have a periodic corrector. So of course it converges nicely. And we also expect the rate conversion is O epsilon because this is bounded. Right? And everything is done rigorously using doubling variable method in the unpublished preprint. So so some of the result on the rate conversion in the past 20 years was listed below. So usually in the literature, people will assume some sort of Lipschitz in the spatial variable locally with respect to P. Otherwise, we have slower rate, and so to obtain optimal rate, it's natural to assume some Lipschitz condition. Right. So the first result is by Kabuzuro, Sessa, and EC in 2001. They use the doubling variable method, basically a PD method, and they obtain the rate of conversion epsilon to the 1/3 for non-convex and multi-scale Hamiltonian. And there's been a lot of work extending this method into different settings. So if you know that if there's a Lipschitz selection of the corrector with respect to P, then we can also improve the rate conversion to epsilon to the 1/2 using the same method. Right, this can be found in the book by Hamilton. So when the Hamiltonian is convex, then one can sort of use method from optimal control theory to study problem in a finer detail from a dynamic point of view. And the first group did this was Mitake, Zhuang, and Yu in 2019. And so this paper, they did more than just 1D, but basically they obtained the optimal rate or epsilon in 1D. And for the multi-scale, it can also, by using sort of the similar method, we can extend the rate or epsilon into the multi-scale for 1D. Then conditional rate like O epsilon can be obtained in some sense generically under some smooth assumption on H bar. And they also obtain a array in 2D under some special condition on H. So this is like the very first paper that utilize optimal control, optimal curve, and look at the problem from the dynamic points of view to obtain the rate. So later on, the problem was fully solved recently by Zhang and Yu, using the special tool, so the Burgo lemma and then the metric distance, right? And they fully solved the problem for the period case with single scale, but we can call it the single scale, and then later on extended to the multi-scale for both time dependent and the scale problem by UC Han and Jiong Zhang here, also using Burgo lemma. So when the potential is not periodic, there's not a lot of work in the literature that address this problem. So the homogenization to the qualitative, right, for almost periodic. So conversion Ho, homogenization Ho is given by Ishii in 2000. So I think the picture can be sort of looking at this. So we have periodic, and then we have almost periodic, and then sort of random. And what does it mean by random? There's a different name, but we don't talk about it in this paper, right? So so just away from the periodic setting, then there's only I think the qualitative result is given in this paper, and then there's one paper where they sort of using the method given by Capsule-Sesta, by Armstrong, Gallagher, and Suganidis. They give a modulus, sort of like adapting this method and give a modulus. So with a modulus, and of course the OS to the 1/3 is a sort of like a drawback, the best we can get. So the interest of our group is coming from this, and we're trying to see if we can use like an optimal control method to obtain an algebraic rate conversion for the for this problem. So let me sort of stating the setting of the almost periodic, right? So the definition people usually use for almost periodic is given a function f which is bounded uniformly continuous, and we consider the family of translation. Then if the family of translation is relatively compact, then this will be the function we call almost periodic. And this property is also called uniformly normal, because there's more than one way to define almost periodic. Right. So for the more common example is in one dimension. If we take the classical mechanics Hamiltonian, and then the potential is given by this function, right? So it's a sum of two periodic function with an irrational frequency, right? So in short, this function is fixed into the setting of the thing called quasi-periodic periodic potential. So the quasi-periodic function is when we just take a function f. Actually here, maybe you can just define it to be continuous, a continuous function on the torus of k dimension. And we take C to be a non-resonant vector. A non-resonant vector means if we take the dot product with any K1, K2, it's kind of not a good notation here, but if we take the dot product with any integer vector, it's never be zero. So we are non-resonant. So typically irrational vector we will satisfy. Then we will say this is the quasi-periodic of K frequencies. All right, so within this setting, then one can prove that homogenization Ho and everything correct, with the exception that instead of the exact corrector, right, Ishii came up with the notion of almost corrector That means the cell problem now is stated in the following way. For every delta bigger than 0, then we can solve this problem with a V delta. Then X bar is a unique constant where we can solve it for every delta. Right. So as I mentioned earlier, so we still have this kind of answers, right? So where V is the corrector. So in this talk, we will see that when in the periodic setting, V is bounded. So in the almost periodic setting, in the case where we can solve this problem, then V might not be bounded. And then we will see that so if we look at this, so the condition we need is basically V over X epsilon converted to 0 at epsilon tend to 0. So at least to make the homogenization whole, right? So this condition is translated in the way that V is sublinear at infinity, right? So we see that the rate conversion is now related to how is the corrector decay at infinity, and we introduce tool to quantify that. All right. So next, so instead of using the definition of almost periodic in the previous slide, we gonna use a different definition of almost periodic, which is more kind of more suitable in the one-dimensional setting. The previous definition is the easiest one to stay in Rn in high dimension, because you just translate the family of translation can be defined in high dimensional easily. So, but in one dimension, this definition is very natural because it's similar to periodic, right? So for epsilon bigger than 0, we call tau is the epsilon period if the translation from tau with the original point have error less than epsilon for every x. So it's very similar to periodic. It just have an error now. So then we say the set we call the set of all. Yes.
Yeah. Starting from here is very new for everyone, so you should go
Yes.
slowly. Yeah. Thank you.
Okay.
It's
Thank
new
you.
for everyone. Yeah.
Yeah, so this is the first definition of homoperics was studied in the literature given by Bohr, right? All the definition were kind of after. So he extended it in the way that is very natural to periodicity, right? So I'm going to repeat again, right? For epsilon bigger than 0, we will call tau is a epsilon period. If f of x plus tau minus fx less than epsilon for every x, then we say the set of all epsilon periods, we denote it by E of epsilon f. And here, I think I forgot like a soup of x here. So we just call the set of all epsilon period to be E epsilon f. Then he defined a function f is almost periodic, written like AP. Like if for every epsilon, for every error, we can find a constant L epsilon such that any interval of length epsilon will contain an epsilon period. So in a different language, he will say that this set is relatively dense in R. Or we can just understand that every interval of length epsilon will contain an epsilon period. So we also call epsilon is an inclusion interval length of FF. It's kind of a clumsy way to say it, but that's historically how people defined it. And then he wrote a whole book going on more property about this kind of notion. And there's a lot of people after him study this kind of property and extended it. So notable, like the most sort of important property of almost periodic function is the existence of the mean value. Right? So if the function f is almost periodic in this sense, so in this sense, sometimes they also call uniformly almost periodic. Right. So a function is satisfy this property, then it has a mean value. I mean, if we take the limit 1 over t of 0 to t, it also is equal to the limit of 1 over 2t minus t of fx. It's also equal to the limit of t tends to infinity of any a plus t fx. So if we take the integral of f on any interval of length t, right, and then we let t tend to infinity, then it converges to a number, and this actually a uniform in A. But for our purpose, this is not very important technical stuff. Okay, and one can see that if in the case of if f is just periodic, for example, right, then the mean value is just the 1 over L in integral of f, right, where L is the period. So it's sort of a natural generalization of a periodic function. All right, so when f is quasi-periodic, which is a smaller class of almost periodic, then we can write out the mean value. Right, so we can write out the mean value. So here, actually, if L equal to 1, then it's just the integral over the torus. So it exactly like so kind of consistent with our generation over here. Okay, so so if it with the quasi-periodic of n frequency, right? So C in Rn and F in C of Tn. Then we have this formula. And so in some sense, we can also think about almost periodic is a function in C of T infinity. There's some notion about this in this book, but how to write it out in like a well-defined sense is kind of problematic. So that's why I only consider quasi-periodic function for simplicity in this work.
Can you explain for everyone? I mean, the last equality, that is easy for you, of course, but can you explain intuitively why is the average
Yes.
of the integral on the whole torus? Thank you.
Yes. So this is sort of like a ergodic theory, ergodic theorem property, right? So in the sense we can see that yeah, this is like f of cx, right? So when c is a non-resonant, that means when t tends to infinity, this will kind of average in time and it keep wrapping and the trajectory become dense in the torus. So sort of ergodic theory property saying we have average in time equal to average in space. So it's kind of connecting the two functions. Rigorously, if we want to see this, then we need, I mean, maybe the minimal assumption is assume f in the continuous on the torus, because otherwise it will be kind of hard to define what is the image along a trajectory in lower dimension. Right? Maybe superlapse space and some trace and will make sense. But for simplicity, let's just assume it continuous. So f of cx is well defined, right? Then to see this, we just have to use approximation by for trigonometry or students Fourier series to approximate for the function f. But yeah, so I think Weierstrass theorem saying that for any epsilon bigger than 0, we can find a polynomial, a trigonometric polynomial that approximates f. Yes, in the C0, right, less than epsilon. So this limits 1 over t, 0t of p epsilon. So when we plug in the trigonometric polynomial, we can integrate every term because they just sine and cosine. So the only term that stand out at the end is the the zero order term, right? And it cancels out with 1 over t over t. So when we take the limit, this is the thing that coming out, and a0 exactly this value is the zero. Is the Fourier transform of the zero frequency of f, right? And then we just let epsilon tend to 0, and then we get the formula, right? Okay, so that is one property. Another important property of homospheric function is how we quantify this rate of conversion, right? So let's come back to the what we call the conversion to the mean value. So let's come back to the period case. So in the period case, when f has a period 1, then the mean value is just integral from 0 to 1 of f on the torus. Then one can prove this estimate, like the rate conversion to mean value is of order 1 over t, and the constant is just the L1 norm of f. And this is the key ingredient to obtain the O epsilon rate. In this kind of work following the method of using optimal control to prove for 1D, right? So in order to obtain something like this, right, we need to find a single estimate for quasi-periodic function, right? So to do this, I found sort of two methods, right? So one is for a general almost periodic function, then we can quantify this with an error. So for every epsilon bigger than 0, then this the error of the conversion will less than epsilon plus the norm of the L infinity bound f divided by t, and this includes an interval, which is the notion we defined earlier in the Bohr definition of homospheric function, right? So if that is the given epsilon, that is the length of an interval where any interval of that length will have an epsilon period. So this is classical, and this is this been written down for like maybe 50 years or more, right? So if we want to go with this route, right, we need to complete the picture. We need to estimate the inclusion as the inclusion interval with respect to epsilon, right? Another way that one can do is in the quasi-periodic setting is if I have higher regularity, right? So if I have f belong to xs of tn, where s is the Sobolev norm defined by Fourier series on the torus, with s bigger than n over 2 plus sigma c. So sigma c is a Diophantine condition. So when we talk about irrational vector, one way to measure how irrational a vector is using Diophantine condition. So the sigma c is a Diophantine index of c if we do the dot product bigger than c divided by kappa to the power sigma, right, for some constant. So these are constant dependent on c, right? So assume that we have a Diophantine index, and then our function f has a regularity big, so s bigger than n over 2 plus sigma c. Then in this case we have like an optimal rate 1 over t, and the constant depend on the Sobolev norm of a function f, right? So it sort of somehow I mean this is good, but this is much worse than the periodic K, because in the K we only have the L1 norm, and so when we do the Sobolev norm, the higher we have to take derivative, the worse it is, because the rate gets worse and worse when we take more derivatives. All right, so these are sort of like a two method that I came up with to quantify this kind of limit. So let's talk about a bit more following the first line, right? So when f is quasi-periodic, then as in the previous slide, we say we want to estimate this. Then the first paper I found in the literature, which is by Naito in 1996, where he's in the case of two frequency, right? So C is C1, C2. Then if omega is C1 divided by C2, I mean, we can take C2 out, and this will become omega 1. So if this number is partly approximable, And partly approximable mean the diamond tie index equal to exactly 1, which is not hard to see that the two are equivalent. Then we can have an estimate of the inclusion interval with respect to epsilon. Yeah, but however, the set of partly approximable is a null set in R, right? So it's sort of like translating into R2, also a null set. Then later on, we can prove that we can find a set of full measure, but then we have to pay a price. That is the experience or another log term. So now basically we can say that there's a set, let's call omega n, where for every Cn in this set, the function f, so the function f(x) equal to f of Cx has this property. Right, so with a factor of log, then we can have a full set of measure. And this result is sort of like truly number theory, but it's pretty cool on its own. Use like kinching theorem, and I have a fun time like learning this. But this the PD talk, so we wouldn't go a lot into this. All right, so using the two result, then we can combine with the technique we have from the periodic case to obtain the result. Here's a main result I first stated for the end frequency, the general case, and then we'll have a prototype where it's much simpler to analyze and it's clearer to see the picture. All right, so given the setting we have, let's say the potential is given by a quasi-periodic setting. Here now I call V to be like some bold V. All right. So then depend on the regularity of the potential. Here I had a typo. Should be 1 to the 1/2. Right. So the because of the p square over here, the subject we consider will be V to the 1/2. It's just directly related to the Hamiltonian. Right. So if V to 1/2 has some good regularity, then we have the lower bound is the negative C epsilon. If we only have the holder continuous, then we can also get the rate, right, for almost C. And finally, using like a result from NATO, that is how we can get rid of the log in some cases. And so that is the lower bound, right? For the upper bound, then we need to assume a bit more. Like if the Hamiltonian is C1 beta with some beta, then we can obtain the upper bound, basically the same bound we had earlier, but now we have another factor. So this factor coming from the holder continuity on X bar. So there's some remark before we move on. So by Sobolev embedding, if this is the case, then we also have V to the 1/2 belong to C alpha, right? Where alpha is the mean of 1 and S minus N over 2. So sort of, if we don't have good regularity, then we still can do that with a log extra. All right, so in the literature, so this is the first algebraic rate for the homoperiodic setting. And also through this work, we sort of highlight the relation between how irrational a vector C and the regularity of V, the interplay between them. And as a byproduct, we also obtain some of the first ergodic theorem, a quantitative ergodic theorem, where so most of the ergodic theorem in the literature is stated for the discrete case. Right? For the continuous case, I couldn't find much reference, but sort of using the result we have here, we sort of obtain some of the ergodic theorem that I'll state later. All right, so here's a simpler case, the prototype that we will use to see the idea clearer. So let us consider the potential, like a two frequency potential, when C just 1 square of 2, and square of 2 is partly approximable. So barely approximable is the one that when you multiply is bigger than K1, K2. Right, so and the power here is 1. So in this case, depend on the power of gamma, right? We have different rates. So if gamma bigger than 2, then we can obtain an algebraic rate of conversion. Whereas the rate is gamma over 2 minus 3 gamma over 2. And we can see that this is sort of belong to 0 to the 1/3. So it somehow is still not going past the benchmark or epsilon to the 1/3 in the literature. If epsilon equal to 2, then we only get a log C over log epsilon upper bound. And this one is one our conjecture that we're sort of on ongoing work that sort of the easiest case, not the easiest case, but the high the case where we have the strongest hope to sort of show it is optimal and show it's like why the rate can be very weak in the quasi-periodic setting. And finally, if gamma less than 2, then we only obtain a lower bound so far. And one can see that in D2K, we have X bar is C1, and this is not. Yeah, and we get the lower bound as at the equation we have over here. Right, so that is the O-level result. So now let's talk about the idea of the proof. Right, so to obtain the lower bound is directly related to how the character of the cell problem decay at infinity. And so this rate will determine the lower bound in the homogenization. On the other hand, like the upper bound depend on two things. Using our method, the upper bound depend on the shape and the relativity of H bar, right? And the averaging of the optimal path, which is sort of like the conversion to this is also called the rotation vector, right? So if we have an optimal path, which is also called the so eta is a calibrated, right, curve, then the average of eta t over t is also it is know that right, is converged to some vector q called the rotational vector, right? And when x bar is differentiable at that q, then this is converged to the derivative. So the upper bound rely on two things: the shape and this rate conversion. Right. So in what follow, I'm going to talk about the shape derivative of h bar, and then we mention the method to get the lower bound and how do we optimize this, and then the upper bound. Okay, so the shape h bar. So in 1D, we can give a better and a clearer representation of the effective Hamiltonian. So to solve the effective Hamiltonian x bar b p, right? We just let it equal to constant mu and trying to solve for a corrector, right? Even though we know that only almost corrector exists, but in this case we can try to solve for the corrector. Then just solving a simple ODE, then we can obtain this formula, right? So if mu is bigger than 0, then we can obtain the formula for right. So this is x bar p. So we can obtain this formula. And of course, this formula is only valid when p bigger than p0, which is p0 will be when we take the constant here to be 0, to Vx. Yeah. Right. So in terms of picture, right, this is p0, which is negative p0. Then for every p outside of the plot part, then we can solve for a exact corrector. And this is something known in the literature, right? Outside the plot part, we have better regularity. So we just said that outside the flat part, we have a exact corrector. Then next, we need to quantify how that exact corrector is sublinear and how is that decay at infinity. Then this is basically using the result we have earlier, right? So the way we construct the sublinear corrector is the sublinear corrector equal to the integral from 0 to x of this function and then minus p of x. Then we observe that this function is exactly a quasi-periodic function, right? So Vx divided by x is exactly the rate conversion of the quasi-periodic function to the mean value. So depend on the regularity of V to the 1/2, we have different rate obtained by two different methods we have earlier. So that does show how we obtain the sublinear corrector. All right, so how do we use it to obtain the lower bound? So it turns out that it's only the correct, even though we only have corrector outside the flat part, but that is all we need to obtain the lower bound, because the part inside with the flat part, it doesn't really play a role. So, all right, so I guess I forgot to write down what the strategy, right? So if we fix xt equal to 0 and 1, then we can write then we can write the solution as an optimal control problem, right? Where we have the first term interaction along the trajectory, and then the initial data adding the average. Then we try to use it to obtain a lower bound. This is from optimal control. Then, right, so the first step is we add the x bar p into the action, and then using the cell problem that we replace x bar p by this Hamiltonian, and then we're using the Fangio inequality, right, to pass into this computation. So now we take the infimum of the equation with respect to all p bigger than p naught, because we only have the corrector when p bigger than p naught, right? So we're gonna lead into this inequality. Then because of if p inside the flat part, then it turns out that this term will be the value of it will less than the value at the corner. So the value of the corner dominate everything in the flat part. That's how we can replace the subprimum to the sub of all p in R. And then this is where the Hoppe formula can be used to, not the Hoppe formula, but that is just the definition of the effective Lagrangian. So, and then the last step is we apply Hoppe formula to get into U0 and 1. So it all come out to this equation, right? So the action bigger than the U01 by Hoppe formula, adding the infimum of epsilon VP of epsilon inverse, right? And VP is a corrector. And now if we can have the decay rate of VP, then we obtain the conversion, the lower bound. So that's exactly the idea how we go. I'll comment more on this at the end, but if we look at this right here, you see that the method is not optimal, because gamma bigger than 2, we have epsilon, right? But if gamma becomes to 2, it's immediately dropped to 1/2. So we expect that the method is not optimal. All right, so to move into the upper bound, we need to talk about the shape of H a little bit. So the most different feature comparing to the period case is X bar can have corner, right? So in the setting that we define, right, we can show that if the potential is periodic, then we most likely don't have corner, and the existence of the corner here will introduce difficulty on the when we try to prove the upper bound, right? So So here's the idea that we try to do the upper bound, right? So also start with the we also start with the action function over a path, right? Then the idea is we're gonna compare this with some sort of average that we guess we can obtain the form, and if we can show that the error of the two about it uniformly for some constant c doesn't depend epsilon, right? Then if we know homogenization holds already, then that's mean in the epsilon limit epsilon to 0, we know that that term has to be u01 and we obtain the rate. So that is the method. So looking into our action function, right? We can write the action function in this way. So we have the average term, and then we have a average of the quasi-periodic function, and then the u naught of the average term again. So if we want to compare this, then we know this, right? Convert to x bar PR if x bar is a differential at the point P. So the correct term that we try to factorize this will be we subtract the mean value inside, and we subtract the rotation vector to the E epsilon R, right? And then we just add and subtract every term correctly. Then here will be the term that we sort of combine it all together, right? So now, if we look at this, to estimate this, we just have to estimate each of the term individually. So the first term is the rate conversion of the quasi-periodic function to the mean value, right? While the second term is a rate conversion of the trajectory to the rotation vector. And if we have those two, then we can obtain the upper bound, right? So here is the why we need to assume a bit more, not just C1, right? So if we have C1, then our Hamiltonian doesn't have any corner. Then in this conversion, right, we don't have to worry about so we don't have to worry that this. So yeah, I think I moved through that a little bit fast, but basically. Okay, so let me come back into this slide a little bit. I'm sorry about that. All right, so when we take a path as a minimizer, for a minimizer, then we have a conservation of energy, right? Then in theory, then we have all the cases that can happen, right? And the case where R is less than or equal to 0 corresponding to P inside the flat part, right? So if our Hamiltonian is flat, is smooth, then we don't have to worry about R less than 0 at all, because at the corner it's only have one value, which is the first assumption, right? So when it is smooth, then if we have a bit more, like a bit extra, then we can obtain also a rate conversion. And this is only depend on the beta, the regularity of the Hamiltonian. So using and the way we obtain this is also again from Fenchel and Young inequality, where we write the Fenchel-Young inequality for x bar p at two different points. We subtract them to get into this inequality, right? So this part it handle it's just the decaying of sublinear corrector, and this part is where we have the C1 beta assumption coming into help, right? If we have those two, then by choosing appropriately the distance b tilde and p, then we'll be able to obtain this rate. And that's it how that's how we obtain the upper bound. For example, here, right? So if we have the C1 beta assumption, and if we have the decaying C over T to the theta, then we can do a balance game of B tilde minus P to obtain this result. And this also explained, for example, in the K gamma equal to 2, then we only have X bar is like in like a C1 log, and it's the optimal, it's a C1 log, so it cannot do any better. So we in turn we get like a log rate, and then by putting them all together, we obtain the result from the 2D in the higher dimension case, and yeah, so that is pretty much the idea and the the result for the work. And I guess we time for questions.
Okay, thank you,
Yeah.
sir. Other questions for Sun before we start deeper informal discussions? So, of course, as you say, can you go back to the result? And I believe that maybe just one, maybe for the prototype case.
Okay. Yes.
Right. So when you say that when gamma is 2, you hope for the rate is optimal, right?
Yes. Yes.
Yeah, and I also tend to believe so. And what I think is that you don't need to stick with the benchmark 1/3 from Kapuzadon-Cheta Ishii, because this is a more general setting, right? So my only question here is that, have you tried the case when the vector is not badly approximable? Would you get a worse rate? Do you expect that?
So I think is included in the second prototype.
Mhm.
Or maybe right. So if this is not badly approximable, then we have epsilon and then a log epsilon cubic.
Mhm.
It's like, so for the case C is C1 and C2 2D. So that's the consequence from the theorem we have over here. So almost all C, right, all irrational, then we have this rate.
Mhm. Right.
Yeah.
Yeah, I was just thinking about, like, exactly for almost all, then you have that, but there can be some very weird vector in which that you can get a worse rate. But then finding that could be very,
Yeah,
yeah.
I see. So yeah, it's quite difficult. Yeah, I see what you mean. Yeah. But trying to find like a yeah, trying to find like a special vector to certify that. Yeah. It's also it's kind of strange because usually when we think about badly approximable, that means we would expect we have the bad rate over there. But
No,
it
no,
turns
no.
out when it badly approximable, we have the best rate
No, no,
using
yeah.
this method. Yeah,
No, no, that we can talk a
yeah,
bit more later. Badly
yeah. But
approximable is good because that implies strong
mm,
mixing.
I
Oh,
see.
yeah, we can chat about that
Mhm.
later. But yeah.
Yeah. So that there might exist some vector where maybe the Diophantine index is very high. That I may expect because I feels like when the Diophantine index is very high, then you need really high regularity in order to have a rate, right? Then that may make thing go badly somehow. But yeah, I didn't know how to. I haven't worked on that yet.
Yeah. Are there other questions for Sun now?
Hi, Song. Thanks for the very nice talk. So I think you partially, I'm not very familiar with the Diophantine approximation, but usually this sigma curse is large. You mentioned, right?
Yes. So the minimum is 1, right? For 2D. Yes.
And
Yeah.
there is no clear control of the sigma curse, no characterization.
So when the C is algebraic, right? Then we can have some control over C, right? I think that's the only thing that's clear, right? But
Okay.
when C is a transcendental, then yeah, it's pretty wild. For example, if
Very.
C equal to pi. I think the record, I mean, this is our curiosity record is like bigger, like 2.6, something like that, which is not too bad,
Okay,
but
so yeah, still not bad.
yeah.
Okay, so then in this results you are showing on this page, the C alpha, by C alpha you mean alpha can be larger than 1 when it's considered as an integer part and a fractional part, or what's the
Alpha
range
is
of alpha?
between 0 and 1. Yeah.
Okay, so then
Yes.
there are some gaps between for Christie that's very large. There
Yes.
are gaps, and do you have does the higher regularity of V1/2 help?
Yeah. Yeah, you're right. So when C is very large, like when the sigma C is very large, they're clearly
Yeah.
gap. Yes.
Yeah.
Yeah. I also, yeah, I think that's also explain one estimate. For example, yeah, I think here when this is gamma bigger than 2, I mentioned this one where going from gamma bigger than 2 to 2, it just jump from order 1 to order 1/2. So I already expected there's some kind of gap in the method I use to quantify this average estimate. And you said it's show even clearer if you when the C sigma is big.
Okay. Thanks.
Yeah, thank you for the question.
Are there other questions? Okay, if not, then let's thank Sun again for this official part. Thank you.
Thank you.